So we're going to talk about the torsional deformation of a circular shaft. We went through this pretty quickly in lecture last week, and so I wanted to give you the full derivation of how we go from looking at the change of angle of twist of a shaft and then relating that to what the shear strain is going to be in the shaft itself. And so the way that we look at this, we're going to start out with the side view of an undeformed circular shaft. And again, like we said in chapter 5, we're just going to limit ourselves to looking at circular shafts only. So only torsional shafts with a circular cross section. So if we have this undeformed shaft, we haven't applied a torque to it yet, and I'm simply going to trace a couple longitudinal lines on the outside of this shaft. So these lines are parallel to the longitudinal axis, just right on the surface of the shaft itself. So when we take the same shaft and we apply a torque to it, I'm going to show the torques here with two-headed vectors. So we're applying a torque to one end, say we have a support on the other end. So we have a constant torque throughout. What's going to end up happening to these originally longitudinal lines is that they're going to start to go at an angle. As we twist the shaft, they're going to start to deform. And so what that new shape is going to look like is something roughly like this. Okay, so these originally longitudinal lines are going to start to form an angle with the longitudinal axis. And the way that we start to analyze this, or starts to try to relate what the shear strain is anywhere on this shaft, is by looking at a small slice. So we take a slice, we're just going to call it a distance dx. So I'm just going to take two section cuts a distance dx away from each other. I'll do the same thing here as well too. A distance dx away from each other. And what ends up happening is if we just take a zoomed in view of the shape that the section cuts on either side forms with the longitudinal lines on the top and the bottom, if I look at both of these shapes and compare the two, what we're going to see is that this shape formed by the intersection of these four lines in the undeformed shaft, that's just simply going to be a rectangle with pi over 2 or 90-degree corners. And so if we were to zoom in to this shape right here, we're simply going to see a rectangle, and all of these corners are 90 degrees, all right, undeformed state. Once we've applied a torque to this and we zoom in on this deformed segment here, we're going to see it gives us our kind of classic shear deformation parallelogram looking shape right here. So now instead of having 90-degree angles in each of the four corners, we end up seeing that we get two acute angles and then two obtuse angles. And we can define how this geometry is changed by using shear strain. And if you remember from chapter 2 when we talked about strain, the way that we would define strain in this situation is I had my original 90-degree angles, and the shear strain is simply going to be that actual change in angle. Okay? So we're trying to figure out how we get to measure this shear strain, gamma, and we're trying to relate that to the actual angle of twist that we see in the shaft, or the change in angle of twist from one section to the other. So right now we're looking at the shaft on the side. We're going to switch it up a little bit, and we're going to start looking at it in terms of on the section itself. So looking in from the left or the right here, looking on end at the section itself. Because what eventually we're trying to figure out is how do I relate, if we looked at a section right here, and say we had we drew a point on the surface of our shaft in an undeformed state, and then we applied some torque to this cross section. What's going to end up happening to this point that we painted on the outside is that it's going to move, it's going to rotate. So let's say that it ends up on the surface once it's been deformed right there. We call this angle, that change in angle, we call that phi. So we're trying to figure out some way that we can relate the angle of twist of the shaft to the amount of shear strain that an element is seeing on the shaft itself, on a cross section in the shaft. Once we can figure out that relationship, then the next step in the next video is going to be to try to figure out the relationship between the internal torque and the shear stress. But this is kind of step number one. Okay, so the geometry gets a little bit complex here, and I have to draw an isometric view, which may be a little bit ugly, but it is reproduced in your book as well too. So the way that we do this is we need to take a look at both the elements from the side and the elements on the section. And we need to figure out a way to relate this angle phi to this angle gamma, because this angle gamma is simply our strain. Okay, so I'm going to do a couple things here. One of the first things that I want to do is from this first section cut on the left-hand side to this section cut on the right-hand side, I'm just going to call this, let's say, section cut number 1. That's the same thing over here. And this right-hand side, we're going to call it section cut number 2. All right, this is section cut number 2 on the right-hand side. So if we think of, let's say, this point right here and this point right here as points that I had painted on the surface of the shaft itself, if I want to figure out the actual distance, the difference in distance in terms of how much more this first section has rotated compared to the second section, I'm just going to define this distance as delta. So delta you could think of as a distance along the surface of the shaft itself. And I want to be able to calculate what delta is based off of this angle gamma and then something else about this geometry. So basic trigonometry, if I want to approximate this distance delta, all that I need to do is take this angle, then multiply it by this distance right here. All right, that distance right there we've already defined as dx. That's distance dx. So then we can just get a simple relationship between delta, gamma, and dx. And we simply say that delta is equal to gamma times dx. Okay? That's kind of step number 1 here, is that we're trying to, first we look at the surface and we try to relate this change in distance along the surface to the shear strain, and it's based off this differential length of this section cut that we've made. Okay, but that doesn't get us all the way there because, like I said before, we're trying to relate phi to gamma. So the next step that we need to do, so this is kind of step number 1. We have our relationship telling us the distance that this point has rotated in comparison of one section cut to the next. And so the next step that we're going to do is we're going to start looking at the cross section itself. And we actually need to look at 2 different cross sections. One cross section is going to be here at section 1. The next is going to be at section cut number 2. And this is where I need to draw an isometric view, and we'll see how that works out. Again, this is reproduced in your book, and so you might want to take a look at that as you're watching this video. So if I were to take this wedge or this section cut right here, take it out and rotate it a little bit so that we could see how the angle of twist of the first section is slightly different than the angle of twist of the second section. That's what I'm going to draw up here. But first I'm just going to draw a section cut of each of them individually. So let's say that we have section cut number 1 right here. All right, we had our original undeformed point right there. It rotated to where that point ended up further along on the surface of the cylinder. If we look at a section cut number 2, what we end up seeing is that we started out with the same location of the undeformed point, but as you can see from this diagram right here, section cut number 1 is rotated more than section cut number 2. In other words, that's kind of this distance right here that we're talking about. section number 1 is rotated more. It's had more of an angle of twist than section number 2. And so what we really care about is the difference in that angle of twist. Okay, so for example, let's say that this may be rotated pi over 4 radians, 45 degrees. Let's say that section number 2 rotated like pi over 8. And so it had some angle of twist as well too. This had some angle of twist. But the difference between these angles of twist is what we really care about, and you'll see why in just a second. Okay, so what I'm going to do is I'm going to take these two section cut views, I'm going to draw them up here in an isometric orientation so we can try to relate phi, the angle of twist, or the difference in angle of twist between these two sections. We're trying to relate that to this distance delta, and we can see that we can do that relatively easily. Okay, so bear with me for a second. Okay, so there's section cut number 1, and then just directly behind it, we're going to have section cut number 2. Okay, we're going to have a longitudinal axis passing through. And from the centroid of this section right here, let's say that we originally started out with a point on the surface that we painted on both section number 1 and section number 2, the same orientation. Okay, but as we applied a torque to this, this point is going to rotate some angle, all right, counterclockwise in the way that I've shown the torque. So this first point on section number 1 is going to rotate, let's say, up to here, okay? And this point on section number 2 is going to rotate as well, but it's not going to go nearly as far. So if I were to draw a straight line between those two, that's this line right here. From here to here, that is this line that we're showing right here. So then I can draw a dotted line across, and then this distance here is delta. That's the same exact delta that we saw over here. It's just that this view is going to allow us to then relate the difference in the change of angle between section 1 and section 2. We'll just call that delta phi. Delta phi is simply the difference in angle of twist of section 2 compared to section 1. And that gets manifested in this change, this difference in distance right here on the surface. Okay, so if we want to figure out the relationship between delta phi and this linear distance delta, it's just like we did over here. If we know what the angle is and we know what the distance is, we can simply say that the change in length at the end of that arc is equal to the angle in radians times that distance. And so the distance that we're talking about here is simply the distance from the centroid of the cross section. So we just call that in general terms rho. So let's say that we're going all the way out to the end. The distance from the centroid, we're just going to use the variable rho. And so I can say that delta in this situation is equal to the distance from the centroid rho times the difference in the angle of twist from section 1 to section 2, which we call d phi. All right, so this is kind of like equation number 2, and you can see that we have a commonality between equation number 2 and equation number 1. So both of these are relating something to this linear distance delta on the surface of the shaft. So now all that we're going to do in step number 3 is we're going to set them equal to each other. And so what we end up getting is that we plug in rho times d phi in for delta right here, and we get d phi times rho is equal to gamma times dx. Okay, so it seems pretty straightforward. We can rearrange this because, like we said before, we're interested in trying to figure out what the shear strain is at any point on our cross section, and so I'm just going to rearrange this equation. I'm going to get that gamma the shear strain at any point is equal to rho divided by dx times d phi. Actually, I'm just going to rearrange that a little bit, move the denominator over to the other side, and I will get gamma is equal to rho times d phi dx. Okay, so we can glean a couple of things from this relationship right here. All right, we can tell that the shear strain at any given point on our cross section is proportional to the distance from the centroid. And so here at the very center of our cross section, actually I'll draw a new diagram. If I were to draw a cross section, and if we were interested in, let's say, the shear stress, or shear strain, I'm sorry, for an element right at the center, the centroid of our cross section, I could tell just from this equation that gamma at the center of our cross section is going to be 0 because the distance from the cross section at this point, or in other words rho, is just going to be equal to 0. We can also tell from this relationship where the maximum shear strain is going to occur. Because it's linearly proportional to, gamma is proportional to rho, wherever rho is a maximum is where we're going to get our maximum shear strain. So our maximum shear strain is going to occur when we maximize rho, and the largest value of the distance from the centroid that we can get is going to be on the very far surface. All right, and this distance right here, that's where rho is a max. It's also known as the radius of the circle. For some reason in your book, they use lowercase c to refer to the maximum distance from the centroid, or the radius. It's just kind of the way that it goes, but this is going to happen on the outside of the circle. In other words, when rho is equal to c. And one other thing that we can get from this relationship right here is that because it is a linear relationship between gamma and rho, we not only know that it's going to be 0 shear strain at the center and the maximum shear strain at the outside surface, we can also interpolate for any point in between. So we can also say that the gamma at any point is going to be equal to the ratio of the distance from the centroid rho divided by the maximum distance of the radius c times whatever our maximum shear strain ends up being. We can interpolate again at the center, rho is going to be 0. At the outside, rho is going to be equal to c, so this ratio would be 1/1. And so we can interpolate at any point in between what the shear strain is going to be. That's going to be important when we start applying Hooke's law to this relationship and start looking at stresses instead of strains, which will be the next video. So again, this is our big takeaway from this derivation right here, is that the shear strain at any given point is proportional to the maximum shear strain which occurs on the outside of the circular cross section, and we can interpolate in between to get the shear strain at any given point. We're also going to use this relationship in a couple of videos to derive how to calculate the overall angle of twist for an entire shaft, and we'll have to do some integration that way. So these are the two things to take away from this derivation here.